Hey, grade 10s. So I'm just going to go over simplifying rational functions in this lesson. So I'm just planning on recording some of the lessons, especially the tougher ones. And I think that this definitely falls under that category. I know that there were a couple questions, so I figured I'd make a video just explaining this. So what we're going to learn about here is rational functions and the key properties that they have, such as vertical asymptotes and holes. And we'll talk about that, how to identify it, and then we're going to look at simplifying rational functions and identifying restrictions. I think this is the top part. This is where a lot of people seem to get confused. So what are rational functions? So rational functions are basically you almost want to think of it as stemming similarly from reciprocal functions. It's not quite the same, but it's kind of a bigger, it basically is a bigger spectrum from it. So what a rational function is basically the formal definition is a function that is of this form. Rx over Sx, where Rx and Sx, so R at x and x at x, are both polynomials. Now, if you're wondering what a polynomial is, there is a formal definition of a polynomial, and you'll talk a little bit more about this in grade 12 advanced functions. So I don't want to go into too much detail, but really all you need to know for now, and again, this won't be like a test question or anything, but a rational function basically has one polynomial function in the numerator and a polynomial function in the denominator. So something as simple as a reciprocal function is still considered a rational function because even one on its own is still a polynomial function, and x on its own is still a linear function, and it's part of a bigger group of bigger family of functions known as polynomial functions. So I'll do a couple examples here. So obviously the first one here, we have x squared minus 4x plus 5 over x minus 2. This is a rational function, and it's a rational function where x is not equal to 2. Now, a lot of you are wondering, what are these restrictions about? This is probably the part that seemed to confuse a lot of you. So I'll explain what that means. A restriction is basically a point at which your function cannot be evaluated. And the reason it can't be evaluated is because if I were to sub it in, I would get a denominator of 0. So you can even try it out yourself right now. If I take this function right here and I were to sub in 2 into x. Now, technically, this means that this will be 2 squared. This will be 4 times 2 and then plus 5. Now, it doesn't actually matter what's in the numerator. That's why you probably noticed that I didn't even bother to evaluate it, because it doesn't matter what value you have. This number right here will be some number that is not 0. But what you'll notice is that the denominator will be 0. And this is where you run into an issue, right? That you cannot divide by 0. And this is why we have restrictions. We're basically specifying that that function does exist for all values except for at 2. So then we set our restriction there. Another example here of a rational function, we have 6x cubed minus 4x squared plus 1 over 3x. This is a rational function because we have a cubic function. And again, you'll learn more about cubic functions next year in grade 12 math. And this is part of a polynomial function still. So you kind of notice that they all, the exponents are the variable is in the base, and the exponents are whole numbers. That's what we already noticed about polynomial functions. And again, I didn't want to go into the whole formal definition of polynomial functions, but all you need to know for now is that they're basically the functions that we've been working with so far, right? Where the variable is in the base, not the exponent. And when the variable is in the exponent, that's something called an exponential function, which you're going to learn about in unit 4. So it's coming up. Anyways, the point is, when we look at this function here, we can see here that once again, there's a point where it's not defined, which is x cannot be equal to 0. And I notice right here, why is that the case? Because if I were to make x equal to 0, then I would be dividing by 0. And you're not allowed to divide by 0. And that's where we run into an issue. So you always have to check, when is the denominator equal to 0? At that point, when the denominator is equal to 0, it means it doesn't actually exist. And this is something called, actually, we think about domain. That's basically setting up our domain, right? It's putting a restriction on what values are allowed into the function. This last one here, I want to trick you a little bit. Why is this not a rational function? So I'm not sure if anyone can see why, but we notice right away that even though it has a variable x, just like the other ones, The issue is that the variable is in the exponent and not in the base. So this is actually not going to be a polynomial, and because of that, it is not a rational function. This is actually an exponential function, by the way, the one in the numerator, but you're going to learn more about that in grade 12. So how do you simplify rational functions? So to simplify basically means making an expression smaller and more simplified. I really don't know how to explain that a little bit more clearly, and I know it's a very simple definition, but what I mean by that is that you're trying to reduce it as much as you possibly can. It's very similar to what you would do with fractions, right? So in the case of rational functions, what you're really doing is you're trying to find a way to cross-cancel common factors. So as an example, I'll give you something easier here. You might remember when you learned about fractions, your teacher would say reduce it to lowest terms, right? So that would mean that you would have to find a number that would go into both of these. And in this case, it would be 4. And so you could divide them both by 4, and this ends up giving you 2/3. Another way to think about this, and I don't think you did this because this would be a little more complicated, is you rewrote 8 as 2 times 4, and you rewrote 12 as 3 times 4. And then you might have noticed that you can actually cancel out the 4 in the numerator and the denominator. And then you end up with 2/3. That's actually another way to do it. You just never really thought of it that way, I don't think, right? Most of you probably just thought of it as division. But really, we kind of noticed that dividing is a very similar process to factoring, right? So this hopefully will remind you of, maybe will ring a bell and remind you that you may have to factor this in order for you to simplify it. Now, in this first couple examples, when we have monomials, you don't really have to factor much. So for the first one here, and this is going back to a grade 9 example, I'm pretty sure I took this straight from a grade 9 textbook. If I give you something like 24x squared and then I divide by 4x, you're going to notice that the 24 and the 6 can actually simplify like this. Well, I know that, well, I could do the math here. 24 divided by 4 is 6, or I can make this even easier. I basically noticed that 4 goes into 24 6 times, so I reduce that to 6, and 4 obviously goes into 4 1 time, so I reduce that to 1. And then I end up with x squared over x, and I notice that in this case, when I have x squared over x, if you think back to exponent laws, hopefully you remember exponent laws here, you'll remember hopefully that x squared divided by x becomes x to the power of 2 minus 1, which becomes x to the power of 1, which you really just can write as x. So we notice that this expression right here just reduces to something very easy, 6x. Let's do another example here. How would you simplify this expression? So we're going to follow the exact same procedure, okay? Nothing too crazy. We're going to look at just the constants that are there. So we take 36 and 12, and we try to see how we can reduce that. Then we look at the powers of x, and we try to see if we can simplify those. And then we look at the powers of y and see if we can simplify those. Well, first thing, we take 36 and we divide by 12. We know that that gives us 3. X to the power of 5 divided by x to the power of 3, that becomes x to the power of 2. And finally, y to the power of 2 divided by 1, y just gives us y itself. So again, you notice that the y is in the numerator and the denominator, but technically y squared means y times y. So you almost want to think of it this way. This just cancels out and you're left with just a y. Same with this. You have x times x times x times x times x divided by x times x times x, which means that the 3 x's in the denominator cancel out with 3 of the x's in the numerator, and then you're only left with 2. Okay, and again, you could use exponent laws to solve this, right? You know that using exponent laws, we can subtract the exponents. So again, I know I'm going a little bit more detailed there, but I'm hoping that you recall this from, I think it was grade 9, you mostly did this, right? But of course, you could apply exponent laws, which, you know, if you have the same base, if the powers have the same base and you're dividing powers, then you can simply subtract them. And so this reduces to 3x squared y, and that's a lot easier to work with. So that's definitely simplified. I hope this is making sense so far. And I think this part of the lesson was not too hard, I think. I'm assuming it started to get tricky when we look at restrictions. So little warning here. This is, I hope everyone kind of knows this, but I just always repeat this because it is a very, 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 very common mistake. If you have something like 5x squared divided by 5, this will actually reduce to x squared. And why is that the case? Well, I noticed that the 5 is being multiplied by the x squared. So that's totally factored out. And I noticed that, again, I can cross cancel out the 5 right there because I'm simply taking 5. Think about it this way. I have like 5x squared divided by 5. And technically, there's nothing there, but if you want to think about x powers of x, you can think of it as x to the power 0. What I noticed next is that I can simplify this to x squared, and obviously 5 divided by 5 gives me 1. So when I talk about canceling out, I just want to be clear. I sometimes talk about cross canceling. I don't want you to think that these numbers disappear, right? I really hope you understand that. It's not that these numbers are disappearing. It's that 5 divided by 5 gives you 1, right? And when we multiply by 1, nothing really changes there. So it has the property, it almost looks like it disappears. It didn't actually disappear. It's just that we're multiplying by 1, which basically means nothing actually changed in the answer. Now, this is not allowed. You're not allowed to take, 5 plus x squared divided by 5 and then cross out the 5. Why are you not allowed to do that? Well, the reason you're not allowed to do that is because this isn't actually written as a product. In order for you to cancel it out, you would need to rewrite it as a product of different terms. So this kind of leads into our next idea that in order for you to cross cancel, you need to factor first, right? You need to express it as a product. That's really what factoring is. I feel like sometimes people overcomplicate factoring. Factoring is basically taking an expression and rewriting it as a product of smaller terms or binomials, whatever it may be, right? That's really all we're doing there. So let's do another example. But obviously now we're going to try to see what else is common. So what if you can't really spot an easy common factor? So what would you need to do? Well, you're going to have to use factoring. And that's exactly what we're going to discuss next. So you look at this and say, well, I could, and it's very tempting, and I understand why people do this. It's very tempting to want to cross cancel the x squared and be like, oh, the x3 cancels out, boom, boom, boom. Wow, this expression is really easy. And then to look at this and be like, wow, I'm almost done. That would be too easy, right? That would not really work out well. And you're definitely not allowed to do that because, again, you're only allowed to cross cancel if it is written as a product. So what we really want to do is we want to simplify this expression and factor it out first so that we can then cross cancel out any common factors, just like we did before. So the first step is that you cannot, and again, just a reminder, you cannot cancel out the common powers. That's not how it works. So you want to factor it out first. So what can I do in the numerator? And again, this is why we spent a lot of time on factoring. I know yesterday a lot of you were mentioning that it was a very long lesson and you were just wondering why we covered so much factoring, so much factoring, so much factoring. It's because you have to get good at it. You have to be really good at factoring. If you struggle with factoring, then the last 3 lessons in this unit are very, very difficult to go through, right? So what we want to do first is we want to common factor out the 3x squared from the numerator. And we notice obviously 3 and x squared is common to both terms in the numerator. So when we cancel it out, when we common factor it out, we end up with x minus 1. What can we do in the denominator? Well, we also notice that 4x is common to all of them. So we take it out and we end up with 2x squared minus 3x plus 1. Okay, what else can we do now? So we look at our expression and say, all right, well, I factored, but it's not fully factored, is it? Right? If you actually notice, you'll see that it's not fully factored. I mean, this is factored here, so I can kind of work with this. This seems to be as factored as I can get it. This is not fully factored. I can probably go lower. So I want to think to myself, how much more can I factor that? Well, I notice it's a trinomial. And if you look at the factoring sheet that was given to us in class, and I think I posted it already, or no, maybe not. It was like a little handout to kind of go over the different factoring strategies. So you might want to look at this and say, well, if it's a trinomial, it's a good chance that I can use sum and product. You always first want to check, can I common factor anything? No, it's not one of the special techniques we learned about, so we can use sum and product. So I need to think of 2 numbers add up to -3, but multiply to give me a times c, which in this case is 2 times 1, which is 2. So can you think of 2 numbers that add up to -1, but multiply to give me 2? So you can think of the two numbers and then you can decompose the middle term. But I'm actually going to show you a different way because I think some of you were talking about the down under method or the Aussie method. I figured I would just go through it with you if that's familiar to you. Again, it doesn't matter which way you use as long as it works. So if the sum is -3, but the product has to be 2, I hope everyone can see here that the two numbers should be -1 and -2. You can check. -1 times -2 is +2, and -1 plus -2 is -3. So that means that my two numbers, which are -1 and -2, will be rewritten over 2. I'm just going to rewrite them over 2 like that. So what I do next in your down under method is you simplify your fraction to lowest terms. In this case, this one's already simplified. This one is not. So I'm going to reduce this to -1/1. And then what you hopefully did is you simply went to the denominator and you put an arrow back and denominator arrow back, and then you simply fill in your brackets accordingly. So you write 2x minus 1 and x minus 1, just like that. And that is how you factor using the down under method. You could definitely decompose the middle term and use factoring by grouping, which we did yesterday, and you would still get the same answer. So in the end, just double check. And again, it doesn't really matter which factoring method you use, just make sure it works for you. What you'll notice is that you end up with this expression here. Now, when I have this, what else do we notice here? What can we do next? Well, the nice thing about this is that we notice that now our whole entire expression is rewritten as a product of different terms. And what's really nice about this is that the x minus 1 and the x minus 1 right here actually cancels out. So those two polynomials, those binomials there will cancel each other out. The 2x minus 1 doesn't cancel out with anything, but we do notice that even right here with 3x squared divided by 4x, that can reduce even more. So what can we do next? Well, the x minus 1, I hope everyone can kind of see that, because x minus 1 is in the numerator, and in the denominator, that actually divides to give us 1. So they cross cancel each other out. And then we end up with 3x squared over 4x times 2x minus 1. Now you can leave it like this, and I'm not too picky. That would be perfectly acceptable. But sometimes teachers may ask you to simplify it even more, which means that they may ask you to actually expand this out and then simplify it a little bit more as much as you can. But I would actually just leave it as it is. I think that that answer is totally fine. So I would just leave it as is. So now we can see here that this is simplified. And actually, I did make one small mistake. I think I should simplify even further. So the x right here will cancel out with the x right there. So I end up with 3x over 4 times 2x minus 1, right? So I actually should reduce it a little bit more. I think I was thinking about that and then I didn't actually cancel it out. So I'll definitely make that change. I'll do that right now. So one small thing, the restrictions. What are our restrictions in this case? Well, and our restrictions, what we have to look at is when is the denominator equal to 0? Now, to be honest with you, I don't think any of you would have been able to look at this denominator and known right away when it would equal 0, right? That's actually not that easy to do. So in order for you to see when the denominator is equal to 0, you need to factor. And that's really, and the good thing about this question is that we actually had to do that anyways. So we almost kind of did this extra work of factoring, but really it's twofold. It's helping us to solve the question, but it's also helping us to find the restrictions. So to factor this out, to find the restrictions, you need to basically figure out when is this denominator equal to 0. So you're asking yourself, okay, when is this equal to 0? This is exactly the same thing as trying to figure out what the x-intercepts are. So if you recall in grade 10 math, I know most of you had Mr. Tancredi, you probably went over how to find the x-intercept of a quadratic function. So if you look at the parabola, you maybe you were asked to find out what the x-intercepts were, the zeros, it's known as different names, the roots, the zeros, x-intercepts. So really what you're doing here is just trying to find out what the x-intercept of this function right here is, the denominator. So to do that, you need to factor. And of course, we go up here and we just factor it out. Luckily, we actually did all the work above. So we end up getting 4x times 2x squared minus 3x plus 1. And that's equal to 0. And I'll reduce it even more. What do we end up getting? 2x minus 1 times x minus 1. And this gives you 0. And then the nice thing about this is that even though it seems like a more complicated question, it's not. All you're really doing here is you have an expression that you know multiplies to give you 0. So you have to think to yourself, okay, if I know that all these terms multiply to give me 0, then really what I'm doing is checking when is each of them equal to 0. Because when one of them is equal to 0, the whole expression is equal to 0. So I have to check when is 4x equal to 0. It's equal to 0 at 0. Pretty easy. When is 2x minus 1 equal to 0? It's equal to 0 when 2x is equal to 1, and then it's equal to 0 when x is equal to a half. And the last one, when is x minus 1 equal to 0? Well, I can solve this pretty easily. I move the negative 1 over, and then I know that this is equal to 0. The whole function is equal to 0 at 1. So even though I found my x-intercepts and I found my solutions, in this case, I specifically do not want my x to equal that because, and again, let's think about why. You don't want it to equal that because what would happen if I sub the 0, the half, or the 1 in here? I end up getting a denominator of 0. And what did we just say at the very beginning? Can you divide by 0? No, you cannot. So really what we're doing when we're finding the restrictions is you're checking when is the denominator equal to 0. That's all that really is. I hope that makes a bit more sense. So just watch out for that and make sure that you, like I said, once you factored it, make the denominator equal to 0. So I just want to make a quick change before I forget, because I will definitely forget if I don't make it now, that this will technically reduce to x right here, and this becomes x. Sorry, this just becomes nothing there, like that. And again, this is coming from the fact that x squared divided by x gives us x on its own. Okay, so our next example, let's do another one here. Oops, just save that. Okay, so next example, we have another one to practice here. So, yep. So we have the function 4x cubed minus 16x squared minus 180x over 2x squared plus 10. Same idea. We have to always think, okay, well, how can I factor this out? Well, I know I can factor by simply common factoring first, right? Which is the case in both of them. I can common factor out the 4x in the numerator, which gives me 4x, and then in brackets x squared minus 4x minus 180. Now, mind you, I'm not showing any of the work. Oops, sorry, not 180, 45. I'm not showing a lot of work now for common factoring because I assume everyone knows how to do that. But if you're still struggling with common factoring, just remember that to find out what the terms are inside the brackets, all I'm really doing is simply dividing each of my terms by the common factor, right? That's really what I did here. I just didn't show the steps. So I took each of the terms and divided by my common factor. That's really what I was doing there. I just didn't show the work. So what we notice is obviously this cancels out. Like I said, x cubed and x cancels out, and x squared and x cancel out. Sorry, the x and x squared and the x cancels out there. So this actually reduces to 4x times 4x squared minus 4, so that's a 1, minus 4x minus 45. So this is what it ends up being factoring to. And the one at the top is actually pretty easy. You factor out the 2x, and then you're left with x plus 5 in the brackets. Okay, so what else can we do? So it doesn't seem that clear if there's anything else I can cancel out, but there is a small thing I can cancel out. The x and the x cancel out. And of course, the 4 divided by the 2 gives me 2, which is nice and easy. So what I'm going to do now is I'm going to try to factor this even more. I'm going to try to see if I can factor that trinomial there. And you might notice that this is actually, this is going to be a simple trinomial. And it's a simple trinomial because the leading coefficient is 1. So the next little step is I can factor out the 2x and, sorry, I can divide 4x by 2x, which gives me a total answer of just 2. And that's how this reduces even more. It just reduces to 2, which is a nice, easy number to work with. And what's really nice here is that I can simply factor this this simple trinomial. So x squared minus 4x minus 45 can factor pretty easily. So I'm going to do this on a separate step here. So we notice that the sum is -4. The product is -45. So what adds up to -4 but multiplies to give us -45? So that would be x minus 9 and x plus 5. And what's really nice about this, and again, one thing you'll notice is you will definitely know if you're doing this right or wrong, if you can cancel things out or not. I am not going to give you a question on the test where nothing cancels out. I will make sure that everything everything is canceled. Sorry, not everything. That there is going to be at least some cancellation of factors, right? I wouldn't give you a question where nothing cancels out, because that wouldn't be a very useful question, right? And by no means. So in this case, what we notice is that the x plus 5 and the x plus 5 cancels out, and then we end up with 2 times x minus 9. And again, this would make sense. Like I said, that the factor would come up in the numerator and denominator because we want it to cancel out. We want something more to cancel out other than just the x. And then we end up with something that's really nice and simple to work with, 2 times x minus 9. And of course, 2 times x minus 9 is, you can even simplify it even more. You can multiply out the 2, and then you end up with 2x minus 18. But I would just leave it like that. You could also leave it factor. That's no problem at all. So that is basically how we how we simplify this expression. What about the restrictions? So for our restrictions, remember, we just check when is the denominator equal to 0. So when we check when the denominator is equal to 0, remember, we only check this one here, 2x squared plus 10x. When is 2x squared plus 10x equal to 0? We don't actually worry about the denominator, the numerator, when that's equal to 0, because again, the numerator can equal 0. There's no rule that says, that 0 divided by some number that's not 0 is impossible, right? You can divide anything. You can divide 0 by any number. There's no rule on that. It's just that you can't divide by 0, right? And I don't want to go into all the details about that. We definitely don't have time for that. But this is something you're going to learn about in calculus. There's a reason why you cannot divide by 0. It's a very important property that we have in math. Essentially, it's not necessarily you can't divide by 0. It's just that the answer will actually go towards positive infinity, which means you can't really approach it. So really what we're trying to do here is just check when do I have an impossible evaluation, right? When is it not going to be possible to evaluate this function, which is basically like looking at domain, right? Restrictions on the domain. So what I want to do in this case is I simply want to make this equal to 0, and then I know I can solve this quadratic equation by factoring out the 2x, and then this gives me x plus 5, 2x times x plus 5, and then that means that I have to check when is 2x equal to 0. Well, 2x is equal to 0 when x is equal to 0, pretty easy. And when is x plus 5 equal to 0? X plus 5 is equal to 0 when x is equal to -5. And you are done, okay? So there are your two restrictions. So the big conclusion here for the domain of a rational function is basically always going to be real numbers, but there's an exception, right? And this is where it gets kind of tricky compared to linear and quadratic functions. So if you recall, linear quadratic functions, the domain was XCR such, and there were normally no restrictions for linear and quadratic functions, right? Unless it was a word problem. It was usually XCR or YER. Pretty simple kind of, XCR, not actually the range was not always unlimited, at least for quadratic, but the domain for linear and quadratic functions is always XCR. For rational functions, we're more limited. It's not just going to be XCR. There's always going to be, not always, but there will usually be an exception in which we will state such that x cannot equal whatever number it is that we have. And again, the numbers that make the denominator equal to 0, and I'll repeat this again, the numbers that make the denominator equal to 0, those are the zeros of your function. So that is going to be your restriction. So I hope that kind of makes sense. So these numbers that make the denominator equal to 0 are the zeros of the denominator function, and these are going to be your restrictions. So to simplify and find the restrictions, you will often need to factor if it's a binomial, trinomial, or anything, if it has more than one term. If it's a monomial, like the first examples we saw, so going back to these ones, just want to go back to the first one so you can compare. Oops. So in these examples, we didn't have to factor because these are monomials, right? A monomial divided by a monomial. That's just one term. But it was with the binomials and the trinomials that we had to factor out, or anything more, basically anything more than one term you had to factor out. So I hope that kind of makes sense. And that was a big kind of conclusion here, right? So the numbers that make the denominator go to 0, those are your zeros of the those are the zeros of the denominator function, and those are also your restrictions, right? And that's the big ticket item here, right? That you have to understand. These are your restrictions. Okay. So what do the graphs of rational functions actually look like? So we talked about how to simplify them. What do the rational functions actually look like? Well, there's kind of two special things that they will have, well, three actually technically. So going back to reciprocal functions, I hope you kind of remembered that reciprocal functions have a vertical and a horizontal asymptote. And if you recall, I actually mentioned that we would discuss it a little bit. So we're going to start discussing it. But I don't want to go into too much detail about rational functions because this is something that you will talk a lot about in grade 12 math. So I don't want to go into too much detail about it now because you'll see a lot more of this in grade 12 math. But for now, if you kind of just want to play around with this and see what it looks like, we can clearly see here that this rational function looks something like this. And if we get closer and closer and closer and closer to our y-axis, sorry, our x-axis, you'll notice that you get very, very, very close to a y value of 0, but you never actually approach it. And same likewise, when x as x gets closer and closer to 0, we get closer and closer to the y-axis, but we never actually fully reach it. So we kind of have a point where the graph technically doesn't exist, and it looks like it's almost going to exist there, but you can even check yourself. It will never actually equal 0. It gets really, 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 really close to it, but it never fully reaches it. And even if I go all the way, I don't even have to go that far. If I just go down to, negative 30 or something like this, you can see here, I get very close to the x-axis, sorry, the y-axis, but I never actually fully reach it. So this is called a vertical asymptote. So the line that we never reach vertically is called the vertical asymptote. The line that we never fully reach is called the horizontal asymptote. So we get very, very close to it, but never actually fully reach it. Rational functions, they may have vertical asymptotes, and this is the key word, may have them, when the denominator s at x is equal to 0. So when the denominator is equal to 0, then you may have a vertical asymptote. It's not always going to be a vertical asymptote though, and we'll talk about this. So for example, if I have something like 6x minus 5 over 6x minus 3. So this is actually what the function looks like, but I'll actually show it to you in the link here, and we can actually look at it and kind of do some comparisons here. So this is what the graph looks like. So what's special about it? Well, let's see here. We have, and I'm going to make this bigger. Let's see. Well, it seems like so instead of our vertical asymptote, instead of our horizontal asymptote being at 0, it seems like our horizontal asymptote has moved a little bit. And what's the number that we seem to get closer and closer to? So I'm not sure if you can see that. Which number do we seem to be approaching? Does the graph seem to be approaching as x goes towards negative infinity? Notice that we're getting closer and closer to 6. So I'm going to zoom out and I'm going to go back in, but I'm going to go the other way around. Let's see what happens on the other end of the function. So what happens as x gets to a really, really large positive number. So I get closer and closer to, again, 6. So not a coincidence. Does anyone want to take a guess why it could be 6? Well, I'm not sure if you're able to look at this function here, but it almost seems to stem from the fact that the leading coefficient here is 6, and if we divide this by 1, we end up getting 6. Again, this is a bit tricky, and you're going to learn about rational functions anyways next year, so I'll kind of leave that for later on. But let's look at the vertical asymptote, because we can at least work with the vertical asymptote, right? So let's see what the vertical asymptote is. So which value do we get closer and closer to, but never actually fully reach? So what's the vertical line we get closer and closer to, but never actually reach? Let's keep going up and up and up. Let's see what happens. Anyone notice what's happening here? Which x value are we getting closer and closer to, but never actually reaching? We're getting closer and closer to 3. And if I zoom out and I go the other way around, so I'm going to scroll back down. I'm going to go the other way around. And let's see what happens as my function keeps going down, 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 I get closer and closer and closer and closer and closer to 3. So I think I can confirm now, especially because I got really, really close to 3 now. And again, you can go even further if you want, but I think everyone can kind of clearly see what's happening here. Our x value is getting very, 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 very close to 3, but never actually fully reaches it. So we can see here that our vertical asymptote is definitely 3. So why is that significant? Well, if you notice, the vertical asymptote is 3, and that matches up with the fact that the denominator has a 0 at 3. So if I sub in 3 into this function, I'm going to get a denominator of 0. And we know that we can't divide by 3. So that makes sense that on a graph, it makes sense that algebraically, when I sub in 3 into x, I end up getting an undefined answer, right? I can't actually solve it. And so that kind of makes sense on our graph that if I were to sub in 3, if I were to get closer and closer to 3, I can get very close to it, but I can never actually reach it. So vertical asymptote kind of matches up with the fact that algebraically, I can't actually sub in that value, x is equal to 3, because it makes my denominator equal to 0, which we know is a big no-no, right? We're not allowed to do that. We can't make the denominator equal to 0. So what we really notice here is that my vertical asymptote, I can even draw it here for you. It's not a very good line there, but my vertical asymptote is at 3 right there. Does that make sense so far? And again, the horizontal asymptote, don't worry about this. We won't really talk about it too much. I really want you to mainly focus on the vertical asymptote. That's what we're going to focus on in on this test at least, right? And again, it's just going to be a few questions on that, but I really want you to understand what a vertical asymptote kind of graphically means and how you can know that just by looking at the equation like that. So there's another special feature. So let's look at the other special feature. So if I ask you to graph this function out, what do we notice? So I'm actually going to show you what the graph looks like. So first of all, it looks like a straight line, which is kind of weird because we probably expect it to look like a reciprocal function, something like that, right? A little bit crazier, and it's definitely not crazy at all. It's actually a relatively easy graph to read, to see. It's just a straight line. Why is it a straight line? Well, we'll notice that the x minus 3 and the x minus 3, those two factors actually cancel each other out. So the x minus 3 and the x minus 3 actually cancel out, and that leaves us with a relatively easy function to work with, which is 6x minus 5. But it's a linear graph, but it's not your regular linear graph. There's one special little feature to it. And what you'll notice is that if I get closer and closer to x is equal to 3 in this graph, and I can even zoom in, I'll show you what happens here. So let's say I click on this graph and I just try to zoom in. Let's just go across and see what happens. As I get closer and closer to 0, I'm going to notice something strange. Look at my function right here. So look really carefully. When x is equal to 0, what happens? I think I keep missing it. Hold on. Just watch out. Oh, did everyone see it? So when x is equal to 0, I end up getting a value that says undefined. And I'm going to make this easy for myself. Instead of me dragging it back and forth, I'm simply going to let x equal 3, and let's see what happens. You can actually see here, and to be honest with you, we can't even click on it fully because it doesn't exist at all, right? That's the other issue that we see with this. So we see that this is an undefined point, which means that we can never actually reach it, right? So even though the function does exist for every single point on every single real number, we notice that when x is equal to 3, we get really, 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 really close to it, but we never, again, we don't approach it, right? This value doesn't exist there. And it's kind of, and like I said, even if you zoom in, you really can't see it much. You would actually have to click on the graph to notice that it's actually undefined there. And why is it undefined? Why can't I just sub in a 3? Well, because if I sub in 3 here, I end up getting a fraction where I am dividing by 0, right? Because 3 minus 3 is 0. And you are not allowed, once again, you're not allowed to do that. So we do have another point that is technically a no zone, right? Like we're not allowed to actually sub in a value there, but it's not a vertical asymptote, which is different than the other case. It's not a vertical asymptote, but it simply just makes the denominator, it still makes the denominator equal to 0. So in this case, the common factor x minus 3 makes this rational function simplified to a linear graph. But the only difference being that when x is equal to 3, the graph is undefined. You actually can, and like I said, you scroll over it and you're going to see there is no point there. So this point is actually called a hole. And the reason it's called a hole, the name kind of says it itself, it's simply a hole in the graph. So if we look at this function here, I'm going to zoom out so you can see it more properly. This is really, like I said, this is the graph of 6x minus 5. And if you don't believe me, if you're wondering, like, how do you know it's the graph of 6x minus 5? Well, let's just type it in and see what happens. Notice that it's the exact same graph, and I'm going to switch the color so you can see it. I get the exact same graph. So if this goes back to a little bit of grade 9, remember in grade 9 to graph a linear function like 6x minus 9, I simply have to start off with the y-intercept, which is -5, and then I have a slope of 5, so that means I go up 1, 2, 3, 4, 5, and 6, and I go 1 across. So I end up right there. So if you look at this graph here, having a hole of at x is equal to 3 means, it simply means that this graph, when I sub in x is equal to 3 here, I'll erase this. So if I go all the way up to x is equal to 3 right here, I go all the way up to this graph, I'm going to notice that when x is equal to 3, I'm going to have a hole. Basically, it's going to be a point that it doesn't actually reach, right? It's going to exist for every other point except for that little spot right there. And again, you can't see it as an actual hole. When you zoom in, it doesn't even look like anything. It's because it happens in a tiny, tiny, tiny little instance. It only happens when x is equal to 3, which I know you would think, you'd be able to notice it more, but you can't, because really what's happening is you're essentially saying that at 2.999999, or whatever, I'll continue this number forever, you get a value you get a function that still exists, but right at 3, it doesn't exist. Now, I'm getting a little too theoretical. Let's go back to basics here. For what you need to know for your test, all you really need to know for the test is that there's two types of points, two types of special features you can have in a rational function that we're going to focus on. There's more, but we're going to focus on two special features, a vertical asymptote and a hole. So the rule here, to check for the general properties of a rational function, like I said, what you're doing is you're finding the zeros of the denominator. Again, what are the zeros of the denominator? The zeros of the denominator are simply when the denominator is equal to 0. So you have your function in the numerator and your function in the denominator. And you're simply going to make s at x equal to 0, and you factor, and you're just checking when is it equal to 0. So if you have a factor, when you factor it out and you have a factor that shows up in the numerator and the denominator, which means it can be canceled out, then you have a hole. And if you have factors that do not cancel out, keyword there, do not cancel out, then you have a vertical asymptote. So another little small example here, just so you can practice with this. If I have something like x minus 3 over x plus 4 divided by x plus 4, this means that you have a hole at x is equal to -4, right? But if I give you something like this, x plus 5 times x minus 3 divided by x plus 4, this is still an undefined spot. So x is equal to -4 is a point where it doesn't exist. But I noticed that it's a vertical asymptote now. And why is it a vertical asymptote? Because nothing actually cancels out here, right? This x plus 4 doesn't cancel out with any of these factors here. So the domain, basically what we do is we basically say that x can be any value, but it can't be a 0 in the denominator. That's what we have to specify. And for the range, we basically say that it's not a horizontal. It's any real value except the horizontal asymptote. But to be quite honest, I won't even bother you about that. Okay. All you really need to know are the restrictions and be able to tell whether the restriction is a hole or a vertical asymptote. That's really all you're doing. And that is it for this lesson. So I hope that made sense. I hope that made it a little bit more clear. All right, best of luck.